Greetings and welcome back. So remember what we're doing. We're in the process of thinking about hydrodynamics, fluid mechanics of the Newtonian fluid. And rather than solving a full boundary value problem that involves the full Navier-Stokes equations at high Reynolds number, we're going to tackle a very interesting problem having to do with Chara, which I already introduced in a previous vignette. So just as a reminder, these long segments here are single cells, and as you can see in this diagram, they have a diameter of about between 200 and 1,000 microns. And as I showed you in one of those videos, there's a motion such that on one side of the cell, the motion is upward, on the other side it's downward, and there's a zone of indifference between those two regions. So this is an interesting example of sort of a classic measurement, which I really admire. You can see on the right-hand side in part D. And what's shown is basically the velocity profile as a function of distance from the surface. And that's the kind of thing that we're going to try to work out. In other words, there's a series of arrows right here. And what I want to do is I want to see if we can use the equations of hydrodynamics that we worked out earlier in order to rationalize, to understand them, and even to make predictions about things like the velocity gradient and what kind of shear stresses are in play and so on. So that's the idea. I wanted to say a little bit about the mechanism, and I mentioned this a bit last time, but just to reiterate, the concept here is that there's actin filaments, which are aligned along the long axis of this cylindrical cell. And in a later vignette, I'm going to talk about the forces that lead to that alignment. For the moment, I'm going to take it as given, and I'm going to go even further. The motors that move along those filaments entrain the fluid in their vicinity, and we're going to represent that strictly through the action of boundary conditions. So I'm not going to worry about the helical pitch of this cell. Instead, we're going to do the simplified geometry that I show you here, where on the right-hand side, we're going to imagine all of the all of the fluid elements at the boundary are moving up with velocity v0, and on the left side, they're all moving down with velocity v0, and we want to work out that boundary value problem. I wanted to take this as an opportunity to foreshadow the idea that we're going to be very interested in, which is how do we impose activity? How does active matter distinguish itself from inactive matter or inanimate matter? And here's a bunch of different ways that this will manifest itself, and that we as theorists, if we're wearing our theory cap, might actually characterize the activity. So as you can see, the current example is going to involve velocity boundary conditions. So, that's basically from the external world putting in a perpetual motion machine. I can harvest the velocity in order to lift weights and things like that. So there's clearly activity, but we're kind of dodging that question by letting it take place just by virtue of the boundary conditions. The next example, which I'll talk about also, is that the rate constants violate detailed balance. You'll remember the detailed balance says the probability that you're in a given state times the rate at leaving that state to go to some other state has to be equal to the probability of being in that other state times the rate constant of leaving that state and coming back to the original state. And the idea in such a case is that you will have no net currents. And here, we'll talk about later about violations of detailed balance and how that actually gives rise to the effects of activity that we're interested in. The bottom left shows you the idea of new terms in the flux. Here I'm just showing you a bird flock, and these are active agents where they have a forward velocity. And the final example at the lower right is active stresses, which I'm not going to talk about just yet. So I wanted to just quickly remind you that last time we talked about the Reynolds number, and I might be using slightly different notation this time, I can't remember, but this is telling us that what we want to do in order to estimate the Reynolds number is we want to take the characteristic velocity scale U, the characteristic length scale L, the density, and then divide by the viscosity. And so let me just give you those numbers. So the characteristic velocity scale is the velocity at the edges, which is 100 microns per second. So I say here 100 times 10 to the minus 6 meters per second. Next, the length scale. Well, the diameter of this thing is of the order of 1,000 microns, so that's 1,000 times 10 to the minus 6 meters. The density is 1,000 kilograms per cubic meter. And finally, the fluid viscosity is 10 to the minus 3 Pascal seconds. And that leaves us with this dimensionless number of 0.1. So it's not super low Reynolds number, but we're in the low Reynolds number regime. And I want to make the claim, so why do I show you this series of differential operators? You know, it's fun to derive these for yourself, and I highly encourage you, for example, to derive this one. You know, get the divergence, or alternatively get the gradient in polar coordinates. And that's something you can do by using the fact that x equals r cosine theta and y equals r sine theta. You can use that, and then, you know, stuff like this. D by dx is equal to d by dr, dr by dx plus d by d theta by dx. That's the way that you'll find the replacements for the Cartesian operators with their corresponding radial and angular versions and so on. So I'm showing you this just because when we confront a spherical problem, then we're going to need to use this column over here, which is spherical coordinates. And so, you know, the Laplacian is going to feature. We saw the Laplacian shows up in the Navier-Stokes equations. If we're in cylindrical coordinates, we're going to need this version of the Laplacian operator. And what I'm gonna claim is that we want to think about the Stokes equation. What is the Stokes equation? The Stokes equation is the Navier-Stokes equations when we turn the left-hand side, meaning the inertial terms, off. And I thought I maybe had written some notes about this, but maybe not. I'm not quite sure. I thought that I had worked through demonstrating, you know, how to think about this. But, well, okay. I mean, the idea here is that, you know, here's the full Navier-Stokes equations right here. And what I can do is I can try to estimate the relative magnitudes of each of these terms. And the thing I'm trying to say, well, you know, alternatively, I can always rewrite this as dv star by dt star plus v star dot grad star v star. I'm just trying to signify that I'm in dimensionless units, is minus grad star. I have a 1 over Reynolds number, p star, and then plus 1 over Reynolds number, and then grad star squared v star. That's another way of writing this. I mentioned this last time, that we could write the equations in dimensionless form, and thus, if my claim is that if re is much less than 1, then we can neglect the left-hand side, and this becomes the Stokes equations, which I show you right here. So here's the problem we need to solve. We're trying to solve the problem of the fluid flow in Chara. What does it mean to solve? It means I want to know the velocity everywhere. Okay, that's what I want to know. And I have two conditions. I have this condition, which is the Stokes equation, and then I have incompressibility. And together, those two make up the set of partial differential equations that I need to solve for this problem. Now, because of the cylindrical geometry, I'm going to assert that the velocity is strictly in the z direction. You see what I'm saying? In other words, I'm saying that the velocity field only has one component, which is in the z direction, and that one component depends only on r and theta. There's no z dependence. So the divergence in cylindrical coordinates just amounts to this, and that's satisfied automatically. So we've already satisfied continuity. Just to show you the divergence, you know, what does it say? Here's the divergence up here, and since a rho and a phi are 0, that, or in my case v rho, which is v in the r direction, and v phi, which is v in the phi direction, since those are 0, these two terms don't do anything. And so all that I have left is dvz by dz. But since vz does not depend on z, I satisfy that equation automatically. So basically the continuity equation is already satisfied. Now, I can write down the Laplacian So I have a Laplacian for VR, I have one for V theta, and I have one for VZ. And so what I want you to notice is that I've already said that VR is 0. I've already said that V theta is 0. Just to remind you, when I say those words, what do I mean? I mean that I have a vector field V. And if I choose to write it in Cartesian coordinates, then it's V1 times the E1 unit vector plus V2 times the E2 unit vector plus V3 times the E3 unit vector. But if I choose to write it in cylindrical coordinates, then V is VR times the radial normal, the radial vector, and then V theta, which is the vector that points in the theta direction, then Vz times Ez, which is pointing in the Z direction. I've already said that there's no radial nor theta dependence to the velocity, and so those two pieces are 0, and what they leave me with is just two simple conditions on the pressure. Okay? In other words, all that survives from this equation is this. All that survives from this equation is that. So we're left with those two things. And then for the Z equation, we're left with this. This is more interesting, more powerful. So there's no gradient in the Z direction on the pressure, and so we're left with this equation. And I'm not gonna go through this because in homeworks you have had the opportunity already to do separation of variables a number of times. So what I'm going to do is I'm just going to walk you through rather quickly the outcome of this analysis, and if you are interested, you can follow my steps. So so the bottom line is that I already have this commentary on the pressure, and so my Z equation is of this form. So I'm going to take the separation of variables ansatz. I'm going to say that UZ is a product of a function of R strictly and a product of theta strictly. I plug this into my differential equation, and I'm left with this thing, which when basically beaten into a simple form, it tells me that I have a function of R, which is equal to a function of theta. And the only way that I can have a function of R equal to a function of theta is if they're both equal to a constant, which with prescience, that's another way of saying done this a few times. I'm going to set this equal to c squared. Okay, and the reason is really just because of this right here. So the t equation is d squared t by d theta squared plus c squared t equals 0. I solve that using a linear combination of cosines and sines. I know that there's periodicity. What I mean by that is if I go all the way around the cylinder, I have to come back to the same place. And so I know that n has to be an integer. Okay? So I've basically got the t of theta, just to be concrete. What we conclude is that t of theta is a cosine n theta plus b sine n theta. N is equal to an integer. And the reason I know that is because of the periodicity. When I go all the way around, when theta is equal to 2 pi, I have to come back to the same value of the function. And so I know that it's an integer. The radial equation now becomes this. So I can redo that by taking this derivative, and I'm going to make the observation that I can solve that equation with a power law. In other words, I make the guess. Just because look at how this thing looks. Here I have no little r, here I have 1 power of little r, and here I have 2. So it just gives me the look of, if I were to take a derivative, I'd lower the value of, so here I'd have r, let's say I have r squared here. Then dr by dr is going to give me an r, but then I multiply that by r, and I'm going to get an r squared. So it's looking like the powers of little r are going to match up if I take a power law. So that's what we do here. And what we find is that alpha, the guess, is equal to n. So here is our solution, right here. So what we found is that uz of r n theta is solved by some coefficient an, rn, sine n theta. Now you might say, what happened to the cosine n theta? The reason I've ditched that is that I know that, let's take a top view of Chara. I know from above, for example, that everybody up here has plus velocity coming up towards me, and everyone down here has minus velocity going away from me. And so I want to basically sine theta is positive up here and it's negative down there. So I know, and cosine would not satisfy that. If I used the cosine, then when I got to an angle like this, the cosine would give me the wrong sign. So now I need to satisfy the boundary conditions, which is what I just was saying. So between 0 and pi, the velocity is upward. It's coming out of the page towards me in this diagram right here. That's this region. And it's minus u0 in this region. So as I say, this is just a classic example of Fourier series for a square wave. And again, you've done, those of you taking the course, I've already had you do some Fourier series things, so I'm not going to belabor this. But the trick is basically always the same. So I have this infinite series. All that I don't know is the ANs. That's the only thing I don't know. And this is evaluated at little r equals capital R. So I actually should have had an R to the n here. So that's a mistake on my part. So the way that you find the Fourier coefficients is always the same. You multiply both sides by sine m theta, and then you integrate. And so I show you that here. That's what this thing is. I can do these integrals. I know that it's a series. That's an orthogonal set, and so the upshot is that I find my Fourier coefficients are 4 u0 over m pi r to the n power. So that's the result. I have the full Fourier series, which is this. So this is the solution to our problem. For steady state velocity, it tells us the velocity at all points r and theta within the cylinder. And this plot from Jan Willem van der Meet, I've already talked about him in an earlier thing. This plot is actually the solution that we just worked out. If you want to amuse yourself, you can show by summing the series. It's a geometric series basically. You'll have to use complex exponentials, but you can show this result, which I think is kind of cool if you want a nice simple closed form, although the series is just as good. Now I wanted to just comment for a second on the measurements. So what I'm showing you here is measurements of the velocity field that were done by Jan Willem van der Meet, and this is awesome and amazing because what we just calculated was this solution, but because this thing is the helical geometry, in other words, it's not perfectly going up and down, but instead it's going like the barbershop pole. As he moves along the cylindrical axis, this whole velocity field is twisting, but the structural form of it is the same as what I showed you up here. So let me just summarize what we've done, because that's basically what I wanted to say about this. So what we've done is we've formulated a boundary value problem to try and capture what I will call, following Jeremy Gunnar-Wardena, our pathetic thinking about this problem. We have this giant cylindrical cell. We know that there's these boundary conditions, which you see here. We want to find the velocity profile everywhere within the cell, and the way we do that is by solving Navier-Stokes. Because we're in the low Reynolds number regime, we neglected the inertial terms. That meant we had to solve just the Stokes equation, which is this thing. I showed you that the equation of continuity is satisfied automatically. I made an assumption about the solution, which was that it's very symmetric, as I show you there. And then we did separation of variables. Okay, I skipped a few little steps here and there. I didn't really talk about the pressure being a constant, and I'm not going to talk about that right now. So we basically solved this PDE. We invoked the tools of mathematical physics in order to find the coefficients in our Fourier series, and we got out this beautiful result, which I show you right here, for the velocity profile as a function of this is as a function of x and y, but you could think of this using our theta and r. So this is the profile that we would get from that Fourier series, where you can see that in the middle here the velocity is 0, and then it's largest and equal on this edge, and then it's large and negative and equal on this edge. And yeah, so it's a nifty solution. So that's what I wanted to say about Chara, and we'll talk later about, let me just foreshadow that, later we'll talk about the forces that the coupling between the actin filament alignment and the velocity field, and how this arrangement of actin can arise spontaneously, which I think is also pretty cool. So that's what I've got on this topic.